Hey math fans, Alex here, and today we're going to consider joint distributions, which are probability functions that depend on more than one random variable. So first we're going to consider random variables x1 and x2, or equivalently, we can consider the random variable x, which is just an ordered pair of random variables. We're going to start off by thinking about discrete joint distributions, and we're going to go and define the joint probability distribution as having the following two properties. Okay, so first property is going to kind of define what it is, and what it is that little p of big x1 and x2 of x1, x2 lowercase, that is going to be the probability, big P, that random variable x1 takes on little x1 and random variable x2 takes on the value little x2. So this intersection symbol is going to be important whenever we start talking about independence. The second condition is the normalization condition, and that basically means that the sum over all x1 and x2 of all these probabilities is 1. And since we have two random variables to consider, we actually are going to have a double sum, okay, where x1 goes from minus infinity to positive infinity, and so does x2. Okay, so we have, if we sum all these up, we should get 1. Whenever it becomes convenient, I'll probably just say like sum over all x1 and x2. Or you could say for all x1 and x2 in r cross r, but only when the notation isn't going to be confusing. Okay, so what I'm saying here is, suppose that we let B go ahead and be a subset of r cross r, okay, which is basically just the set of all ordered pairs xy, where x and y are real numbers. Then we have that the probability, that x1 and x2 belong to B, that's going to be the sum over all ordered pairs x1 and x2 in B of this probability function. Okay, and just to kind of paint you a picture of what's going on here, imagine that this is, the real number plane. This is essentially r cross r, right? And my region B could be just a subset of these ordered pairs, okay, a countable subset. So it could be infinite, could be like all the lattice points, for instance, all these integers, or it could be, these points, that point, I don't know. And maybe all of this is going to be our set B. Well, then in order to find the probability of B, naturally you're just going to plug in all these ordered pairs and then sum them up. Okay, so that's essentially what it is for discrete distributions. Okay, now suppose that x1 and x2 are continuous. Well, we have a similar two properties. Okay, but the first one I'm going to go ahead and put in terms of this subset B. So if B is just a subset of r cross r, then we're going to go ahead and have that the probability that x1 and x2 belong to B, well, this time it's going to be a double integral over the region B. Okay, instead of just summing over all of those distinct points, B is going to be kind of a continuous region, and that's going to be probability x1, x2, little x2, dx1, dx2. So it's going to be a double integral. And the second property, of course, the normalization, is that the double integral over, we'll say, r cross r of this probability function has to equal 1. Okay, so I know I threw a lot at you. Let's just do an example to remind ourselves how to even compute a double integral. Okay, so example 2 says, let x and y be continuous random variables with the following joint PDF. Okay, sometimes you see them symbolized lowercase f, and lowercase f of x and y is going to equal x plus cy squared if xy is in B, and 0 otherwise. And the region B that we're considering is the unit square, which is 0, 1 cross 0, 1. So just to sketch out that region for you, let's say this is 1, and this is 1. Okay, then this is our region, which we are calling B. Okay, so part A is to find this constant C, and part B is we're going to find that the probability that the ordered pair is in the set A, where A is the square of length 1/2. Okay, so how are we going to do this? Well, to find C, we're going to go and use normalization. It's going to be a very powerful tool. Okay, so normalization says that the integral over the entire region has to be 1. So this integral over r cross r over this joint probability function has to equal 1. Okay, but if you look back up to the joint distribution, this is only going to be non-zero if the ordered pair is in B. Okay, and it's 0 otherwise. So really what we can say is we can go ahead and write this as just the double integral over B. Okay, and then if you'll recall, this was x plus cy squared dx dy, and that needs to equal 1. Well, remember that the region B was just the unit square, right? So it's pretty clear how we're going to integrate this. Okay, so I'm going to go ahead and do that. So when I do double integrals, I always specify which comes first. In this case, it doesn't really matter because x and y are fairly independent when it comes to the region B. But I'm going to go ahead and put x first. So x is going to go from 0 to 1. And y is going to go from 0 to 1. And yes, I actually write out x equals and y equals. And we'll have x plus cy squared dx. And this thing is being taken first. And then we're going to integrate with respect to y. That's going to equal 1. Okay, so how do double integrals work? Well, y is considered a constant in this first integral. Okay, so this is going to be integral from y equals 0 to y equals 1 of this guy. Okay, so maybe I'll do that in blue. Okay, well, we have an x, so that's going to be an x squared over 2 when we integrate. And then this is just going to pick up a constant x, right? Because this whole thing is a constant. So with respect to x, when we integrate that, that's going to be cy squared times x. And this is going to be evaluated from x equals 0 to x equals 1. Okay, and that, integrating that with respect to y is going to equal 1. All right, well, the stuff in blue, we only really need to plug in x equals 1, right? Because if you plug in x equals 0 everywhere, you're going to get 0, which is something that you do need to check because of things like sines and cosines and exponentials. But for polynomials, when you always plug in x equals 0, as long as there's not like a plus 5 at the end, you're probably good. Okay, so plugging in 1, we get 1/2 plus cy squared. And we're integrating that with respect to y. Okay, and now when we integrate, this is going to pick up a factor of a y, and this is going to be c times y cubed over 3. Okay, and this is going to, of course, be evaluated from y equals 0 to y equals 1. I should really be writing implies. I don't know if I haven't been doing that. Okay. So now when you plug it in, again, you only need to plug in y equals 1, and then you get 1/2 plus c times a third is equal to 1. And I'm going to go ahead from here and multiply both sides by 6. Okay. Okay, so what do we get? We should get 3 plus 2c equals 6, or c is going to equal 3/2. That's important for computing probabilities, because if you don't know that value of c, then you're never going to be able to integrate that over any other region and get a definitive number between 0 and 1. Okay, so now that we have that, I'm just going to remind ourselves what the probability distribution function was. So remember that that was, well, of x and y, and that equaled x plus cy, where now we know the value of c. X plus cy if x and y was inside the unit square, and 0 otherwise. I think this was a y squared. Yeah, this was a y squared. Okay, so now for part B, we want to now integrate this over the region A, which was the square of length 1/2, right? So we wanted the probability that the ordered pair belonged to A, where A was a smaller region. Okay, well, that's again not too bad. I'm probably going to set up the integral and have you compute it as an exercise, but it's going to be the integral over A now of fxy, little x, little y, dx dy, okay, where A is going to be, okay, so if this is B, then this is A. Okay, so that's going to equal the integral 0 to 1/2, 0 to 1/2 of x plus 3/2 y squared dx dy, and that's going to equal 3 over 32. So this, I'll have you do that as an exercise. And I might actually post a separate video giving you some tips and tricks for double integrals and single integrals, just because, I wish someone would have told me this stuff. But yeah, that's essentially how you do it. So you integrate over a region this time. Yeah. All right, so a couple more terms. First, if we're given random variables x1 through xn, we're going to go ahead and suppose that the events where the random variable x sub k is between little x sub k prime and little x sub k double prime, for all k between 1 and n, are independent for any values of x sub k prime and x sub k double prime. Okay, so in other words, if I say that, x1 is between x1 prime and x1 double prime, and I say that those events are independent for any choice of x1 prime and x1 double prime, and if that's true for all random variables x1 through xn, then we can go ahead and say that the variables x1 through xn are independent. Okay, furthermore, go ahead and let x1, x2, ... forever, let that be an infinite sequence of random variables, which we defined in the previous chapter. And if x1 through xn are independent for every single n, then x1 ... this infinite sequence of random variables, is called a sequence. It's called a sequence of independent random variables. Okay. Now, why am I talking about independence all of a sudden? Well, remember, we have a very, very useful formulation for independent events. Okay, so in practice, this is pretty useful. Okay, so let x1 and x2 be random variables with probability density functions p x1 of x1 and p x2 of x2. These can be either discrete or continuous, but we're going to consider each case separately. Okay, so for x1, x2 discrete, we have this joint distribution function, which we can make arbitrary. Okay, so perhaps we have that x1, x2, x1, x2 is the joint density function. But remember what this is by definition. This is the probability. This is the probability that big X1 takes on the value little x1 and big X2 takes on the value little x2. Where I'm going to go ahead and highlight this intersection symbol. Because if x1 and x2 are independent, that means that for any little x1 and little x2, we must have that this is equal to the probability that x1 is equal to x1 times the probability that x2 is equal to x2. Right? An intersection splits up into multiplication of these separate probabilities if x1 and x2 are independent. Okay, so this is for the random variables x1 and x2 independent. That means that this condition holds for whatever values of little x1 and little x2 I have. For continuous, it looks a little different, but we'll get there in just a minute. But isn't this probability, by definition, the same as the PDF of x1? And this, by definition, is just the PDF of x2. Okay, so we have that for x1 and x2 independent, at least for the discrete case, it looks like the joint probability distribution is going to split up into products of PDFs of the individual events. Okay, so for x1 and x2 continuous, it gets a little tricky because remember, probabilities are only useful when you're describing them over a region. Okay, so we're going to go ahead and define B as the following square. We're going to let that be x1 prime to x1 double prime cross the interval x2 prime and x2, should be a comma, x2 double prime. Okay, then recall that the probability that x1 and x2 resides in B, well, I can write that as the probability that x1 is between x1 prime and x double prime, and that x2 is between x2 prime and x2 double prime. Okay. And there's that intersection symbol. And remember, for continuous distributions, even if I have independent events, I can still write this as the probability that x1 is between x1 prime and x1 double prime times the probability that x2 prime, or that x2 is between x2, like that. Okay, so the intersection essentially works the same way, but the reason this is kind of useful is now let's go ahead and look at what the integrals are. Okay, but this remember, that's essentially the double integral over B, which is going to be from x1 prime to x1 double prime and x2 prime to x2 double prime of the joint density, okay, dx1 dx2, okay, and that has to equal this, which only happens when I can break this joint distribution up as follows. And I can break it up into as the product of individual densities Okay, and the reason that I want to do that is because now this is going to equal the product of, actually, let me do it this way. Let me do it x1 prime, x1 double prime of px1 x1 dx1 times the integral x2 prime x2 double prime of px2 x2 dx2. Okay, so this is by Fubini. I think we give Fubini credit for that. Okay, which is precisely what we wanted. Okay, so basically this condition that x1 and x2 are independent in the continuous sense means what? Well, it means that we can break up this continuous joint PDF as a product of individual PDFs, and this is essentially y. Okay, so just to summarize before we get into our last example, so this joint distribution would equal these two for x1 and x2 independent. So same outcome as discrete, but for very different reasoning. Okay, now let's go back to that example and let's actually see if x1 and x2 were independent. Okay, so example 3, go ahead and recall the joint PDF from example 2, and what we want to know is whether or not x and y are independent. Okay, so what we need is we need to determine if this joint PDF can be written as a product of the PDFs of x and y separately. Okay, but the problem is we don't know what the PDFs of x and y individually are. Okay, so I'm going to show you how to do them. So in general, if you want to find, if you're given a joint distribution of two variables and you want to find the PDF of one of those variables, what you're going to do is you're going to integrate over all possible y values. You're going to integrate this joint distribution over all possible y values with respect to y. And if you integrate over all the possible y values, think of it as taking like infinitely many like separate mutually exclusive events of just y. Okay, maybe writing x as, you know, x intersect y1, union x intersect y2, union, etc., where obviously y1 and y2 are like maybe very thin slices of the real number line. Okay, which you can do. You can take any region of the real number line and you can separate them into countable subsets like this, countable intervals. And you can just kind of sum over all of them, and all you're going to be left with is the event x. Okay, so this works very similarly in the discrete case, although I'm not really going to show it. Okay, but this is called a marginal distribution. And let's go ahead and compute it in this case. Okay, so how are we going to do that? Well, we're going to integrate over all possible y, which you'll remember is just the y's in the unit square. And we're going to integrate x plus, remember we found c to be 3/2 y squared dy. All right. Well, the x is going to pick up a y, and integrating y squared, we're going to get y cubed over 3. We're evaluating that from x equals 0, or y equals 0 to y equals 1. When you integrate this, you should not get a number. I mean, not in general, at least. You should get a function of x, because we're evaluating at y. Okay, so these 3's are going to cancel, and again, all I really need to plug in is y equals 1, and I'm going to get x plus 1/2. Okay, so that's my probability function, my PDF for just x. Now for y, I'm going to do the same thing, but this time I'm going to integrate over all x of xy dx. So this is still a marginal distribution, and in our case, we're going to integrate over unit square, x equals 0 to x equals 1 of x plus 3 halves y squared dx. All right? No. Wait. Yes, dx. Okay, so that's going to be, this is going to be an x squared over 2 plus 3 halves y squared x, because this just picks up an x because it's a constant. And we're evaluating that from x equals 0 to x equals 1. Okay, but that's just going to be, let's see, this 1/2 plus 3 halves y squared. Okay. So, what do we think? Do we think x and y are independent? What does your gut tell you? If this is the joint PDF, do you think x and y are independent? No, but we just showed why. So remember that the joint PDF of x and y, that was equal to x plus 3 halves y squared. Well, that does not equal the product of, what did we get? X plus 1/2 times 1/2 plus 3 halves y squared. You can go ahead and show that really quickly, which is the product of the separate PDFs for x and y. So x and y are not independent. Okay, so joint distributions in general involve a lot of double integrals, which can be really tricky, so I recommend going really slowly when you do those problems. Okay, in the next video, we're going to explore a couple of really interesting examples. Hope to see you there. Have a great rest of your day.